So let's talk about Fourier series. Okay, what are they? But before, and how do we compute them? Of course, before getting into the Fourier series, let's go back and review a little bit of Calc 2. I mean, what was the purpose of a series? Okay, Calc 2. In Calc 2, you cover a very important topic that any function f of x can be equal to sigma n equals 0 to infinity of some a sub n, or actually c sub n, x minus x naught to the n power. Okay, so what is it? This tells us that you can represent any elementary function as a power series. Well, in some cases you may come up with a closed version in sigma notation, but for more elaborate function it may not be possible. So, but at least for the elementary ones that we work, I can calculate like e to the ax, sine of, okay, e to the u, cosine u, sine u, arctan u, even the hyperbolics. Well, there's a closed form for those series in sigma notation. Well, and what else? Okay, so if x naught equals 0, then this is a Maclaurin series. And if x naught is not equal to 0, any other number, isn't that the name of the series? Taylor series, right? Okay. I mean, for instance, e to the x equals, come on, we have used this function a lot. N equals 0 to infinity, x to the n over n factorial, that is, that's 1 plus x squared over 2 plus 1 over 6x cubed plus 1 over, what's 4 factorial? 24? 24 or x to the fourth plus, come on, we infinitely many terms, right? Okay. So where do these series come from and why do we want to use it? Okay. One of the applications back in calculus, so we're going to go back even way back to calculus 1. Okay. So the first two terms right here, which would be, if you want to call it what? P sub 1, all right? P sub 1 of x, which is 1 plus x. So that's the first degree polynomial to approximate the value of the function. But wasn't that just the equation of the tangent line? And what happens when you want to approach if this is to determine if this is a good approximation? So so that is actually the equation of the tangent line right here. And so this first degree polynomial, it's a good approximation for certain neighborhood of values, like I would say maybe around this value. Did you see how the tangent line is very close to the function values in the exponential function? But I mean, if I start go away, look at this distance. So I don't like that distance. Actually, what I'm trying to say, not that I don't like, I mean, what I'm trying to say is that the approximated value and the actual value now differ by quite a big margin of error, as opposed to values that are close to the center value, which is at x equals to 0. So a linear approximation was not the best choice unless you come up with another linear approximation, maybe here, or maybe there, depending on what you want to approximate. So that's one. Number two, maybe come up with what? A quadratic approximation, okay, to decrease the amount of error. Maybe the cubic approximation, maybe the quartic approximation, the quintic approximation. Increase the degree of the polynomial to approximate. And what's the real meaning of this? Okay, I can't draw the quartic and quintic polynomial. However, I have a GeoGebra file here to show you how that works. So for instance, here I have the graph of the exponential function e to the x, okay? And here I have another function that describes its its series form, that is x to the n over n factorial from n equals to 0 to b, where b will be the degree of the polynomial I want to do the approximation for. So let me actually do that, okay? Well, what if I use the 0 degree approximation? I mean, come on, actually it's going to be just an intersection, and the 0 degree approximation will only converge to the function at the center point. What if I increase this to 1? Well, that's the tangent line I was talking about before, right? Well, clearly there's an intersection at the point of tangency, and well, some approximated values are kind of close around the center point. Well, what if I do the quadratic one? The quadratic. Do you see how more points on the quadratic approximation overlap? I mean, overlap is the informal way, but the formal way is to say converge to the values of the function, keep increasing. More values, more values. The higher the degree of the polynomial, the better, isn't it? You see? Do you see increase the degree of the polynomial of the approximation? And do you see how the approximation now starts to converge to the actual values of the, that was the whole point in Cal 2. All right. Keep doing more. Well, I'm gonna do all the way to the Fourier, right? As another example, for instance, the sine function, I did two examples, the sine function and its approximation as a series n negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial from n going starting at 0 going to b, well, whatever the value I choose to give here, right? Okay, so let me start with 0 again. And well, so for 0, there is this diagonal line. So let me increase the values of b to get a larger degree polynomial. Actually, let me do this so you can see the generation of the terms. Actually, it's not going to simplify. It's just going to generate without simplifying. Now, do you see how the more the more terms I add to the series, the approximation, the polynomial converges to the actual function we're trying to represent here, increasing therefore the accuracy of the approximation. So that's what this is all about. Okay. So, and you might you may be wondering, where are we heading with this? Well, Fourier series are also approximations for other kinds of functions. Remember the functions we described in the previous chapter? Those functions with discontinuities, like step functions or functions in the, what's it called? In the periodic, the last topic in Laplace, where we have the periodic functions and the ones that repeat, well, there has to be a way to represent those functions as a series, but we can't do this with a Taylor or Maclaurin series. We need Fourier series for this. And well, while Taylor-Maclaurin series are polynomials of powers of x, Fourier series are polynomials of trigonometric functions, sines and cosines, which, yeah, let's get started with this. Yeah, I'm so excited about this. Okay, so Fourier series. Okay, so, but okay, wait. We're not going to get to compute a Fourier series right away. We need some pieces of information, some tools that we need to sharpen before actually getting to the test. So number one, what are we doing in this section? So we're going to review what even and odd functions are. Some not necessarily shortcut rules, or rather tools that are going to be useful to compute this Fourier series when we integrate odd functions over symmetric domains. And well, because guys, computing a Fourier series could be a nightmare. However, keeping in mind these tools that we're going to review, that's actually going to help us expedite a lot of the calculations, you know? So and then, of course, we're going to compute Fourier series for periodic piecewise continuous functions. Okay, guys, well, so let's talk about even and odd functions first of all. So a function f of x is said to be blank if f of negative x equals f of x. What is it? What's that one? Even, right? Even. And the other one has to be the odd one, right? Come on. Okay, guys. Graphically, we have a graphic representation of even and odd functions, while an even function has a symmetry about the y-axis. An odd function has a symmetry around the origin or about the origin. So if we look at these three graphs right here, which of the functions is the even one? Which of the graphs is the even one? The first one, right? This is the even one. What about the second one? Even or odd? Mhm. This is odd because of the symmetry about the y-axis. I mean, about the origin rather. And the third graph, it's neither. Neither. All right. Okay, guys. What about okay, so the next part is key. It's important to compute Fourier series. Let's talk about the algebra of even and odd functions. For instance, sums of odd powers of x are odd. For instance, f of x equals to x to the fifth minus x to the seventh plus x cubed. Odd power, odd power, odd power. That's going to give us odd function. If you evaluate f of negative x, everything is going to be the value of the function with the opposite in sign. That's going to tell us algebraically that indeed it's an odd function. Sums of even powers of x are even, like f of x equals to, what is that? X to the 6 minus x to the 4 plus x squared. That's actually another even function because negative x to the 6th power is still positive. Negative x to the 4th power is still positive. Times the negative remains there, and x squared, or rather negative x squared, it's still positive x squared. So that's an example. Specific cases like f of x equals to sine, and this should be cosine x, not sine. Little typo here. Okay, what about sine, even or odd? What about cosine? Even. Okay. Okay, here be careful. Product of two odd functions is even. Okay. For instance, maybe okay, two odd functions. So f of x. Okay, let's choose a good odd function. Maybe something like x cubed. Can you think of another odd function? Can you think of another odd function? X to the x to the fifth, that equals x to the eighth, which is an even function. Another example, g of x, which is what is that? Which is another, let's say x, simply x. That's an odd function times sine x. How about that one? Because x is odd, sine is also odd. Odd times odd equals to even. The product of two even functions is even. And again, okay, let me do f of x equals, how about x to the 6 times x to the 8? That equals x to the 14, right? Or for example, g of x equals to maybe x squared. And can you think of another even function? How about cosine x this time? All right, cosine x. All right, the product of an even function and an odd function is odd. So guys, this goes with the same parity as numbers. 2 times 3 equal, the product of it's odd. So that is f of x equals to uh even and odd, it's odd. So that is x to the 7, say x to the 4th. What is that equal to? X to the 11, which is an odd function. What about f of x equals to an even function? X to the 4th times sine x. Isn't that another odd function? Okay, so odd times even, in this case, that's a not one. All right. Okay. Another piece of information in order to generate some of the coefficients of the Fourier series, we need to keep in mind because this cosine of n pi will spawn every more, actually very, very often. Okay, so let's talk about this quantity. So for when n is odd, what's the value of cosine of n pi? Say, okay, keep in mind cosine of pi, cosine of 3 pi, cosine of 5 pi. What is that equal to? What is that? Actually, if it works, look at the graph of cosine. That's pi, pi over 2, 3 pi over 2, and here 2 pi, right? What's the value at pi? Isn't that negative 1? It will be the same at 5 pi, or rather at 3 pi, 5 pi, 7 pi. What about when n is even? What's the value? Positive 1, right? So actually, we can relate this cosine of n pi equals to negative 1 to the n. This is something you may have done in calculus too when you were working on alternating series. You were given an alternating series in this, guys, like, oh, like discuss the convergence of the series sigma n equals 1 to infinity of cosine of n pi over n. And then you were like, wait a minute, there's no alternating factor, right? But in this case, it turns out this is the same as saying negative 1 to the n, 1 over n, and then you do the test, right? That's something you may have done in calculus too. So this is going to be very important and very, very useful. All right. Well, actually, let me leave it here. So, what integrating even and odd functions over symmetric domains. So let's suppose p greater than 0 be any fixed number, be any number. And f of x is an even it's an even function. So here's what happens when we integrate an even function. Well, the easiest case we can think of is the quadratic function y equals to x squared. That's I guess the best example for an even function. So do you guys agree that if you integrate between negative p, okay, this is negative p to positive p, isn't that the same as integrating from 0 to p and then multiply your result by 2? Why do we do this? Because oftentimes um, very oftentimes having a lower limit of 0 would actually help us simplify calculations by a lot, and that's something you might want to take advantage of. All right, so that's case number one. Case number two, okay, what about an odd function? The problem with odd functions, that is the functions that have symmetry about the origin, just output the same amount of area, how it reflected about the origin. But the problem here is the area on the left hand side, well, or at least for this picture, on the area on the left hand side is a negative area. All right, and well, these two areas added together would give us a 0. All right. I know that's kind of a weird thing to say. Well, that's a 0 area. Well, yeah, but they cancel out. Geometrically, I can see that area, but numerically they would cancel out. So that equals a 0. So that's something that I would that will be very, very useful. All right. Okay, guys. Well, the next topic in Fourier series here, it's periodic functions. Actually, we already talked about this at the end of the Laplace transform chapter, but I would like to revisit the definition and then from here connect to the actual Fourier series. Okay. So again, a function f of t is said to be periodic if there exists a positive number t such that f of t plus uppercase t equals to the value of the function f of t. And again, if we say that in general, f of t plus n times the uppercase t equals back to f of t for all n in the integers, because we can multiply a periodic the values, we can add the period right here and we still get to the same y for the same function value. And we discuss in detail how, for instance, the sine function or the cosine function, they are 2 pi periodic. If you evaluate, say, sine of, okay, cosine of 2 pi, that equals to 1. But if you evaluate at 4 pi, at 6 pi, 8 pi, well, 4 pi, 6 pi, 8 pi, those are coterminal angles to 2 pi, and that those would output the same function value. Well, back in the day, we called them, what is that? Coterminal angles. But in reality, well, more formally, well, that's really like the period, right? The fundamental period, which again, that's the smallest positive value t that satisfies the period equation. Okay, examples of what is that? Of periodic functions. Again, sine and cosine functions where sine bx and y equals cosine bx have a period of p equals to 2 pi over b, where b is the number that multiplies the x inside of the angle, right? And then we have the called the square wave, typically denoted as q of t because it's kind of a square wave right here. Typically, you would see these graphs like this. So that's why it looks a lot like a square wave, right? But in reality, those vertical lines I just draw, actually are just the jump discontinuities. We don't need them. So they just go. So this is a function that jumps up and down between -1 and 1 for different values of, or rather multiples of pi or 2 pi. Well, how do we find the fundamental period here? Well, again, see how long it takes for the graph to repeat its shape, essentially. That is, in this case, between -pi and pi, how many units are there? Are they 2 pi? Aren't they 2 pi between pi and 3 pi, etc.? So t, the fundamental period, will be 2 pi. Of course, we can manipulate these intervals to. They're not necessarily have to have a 2 pi period, you know? All right, what about another very common graph, another very common one, the sawtooth wave, W of t, which is the diagonal line t between -pi and +pi, and then it repeats and repeats and repeats and repeats, right? Increases with positive slope, reaches a maximum value of pi, then boom, goes down to -pi, increases, and so on and so forth and so forth. All right. We have another one, the triangle wave. Also, they call it the tent function as well because it looks a lot like a tent, right? And well, that's actually the absolute value of t, the V-shaped graph. Okay, let me actually. This gets just repeated and repeated and repeated and repeated. And for both of these functions, actually, the sawtooth wave and the triangle wave, what is the fundamental period? You guys agree they're also periodic at 2 pi, every 2 pi units? They repeat every 2 pi units, all right? Okay. And these are the kind of functions we want to find a series representation for, can you think about, think about it. There's no way we can represent these functions with these continuities in periodic on top of that using a Taylor series, using a Maclaurin series, because these are actually, most of them are t to the first power. So the minute you take a derivative, you get to zero after the second derivative, right? So there's no way uh, we can uh, we can express this. So for this, well, these are the kind of functions that you will see in electrical circuits, in signals, in sound synthesis, like music, creating music electronically, and well, again in electronics, and many many other areas that actually use this these periodic functions. Okay.